Unit 7, pages 216 to 220, slope fields, graphical representations of solutions to differential equations. A slope field is a pictorial representation of all possible solutions to a given differential equation. Remember that a differential equation is the first derivative of a function, f prime or dy dx. Thus, the solution to the differential equation is the function f of x or y. There are infinite number of solutions to the differential equation dy dx equals x minus 3. We're going to show our work and explain why. So we start with the differential equation dy dx equals x minus 3. So to find the solution to this, we have to first separate our variables. So we have dy equals x minus 3 dx, and then we integrate both sides. The integral for dy will give us y. The integral for x minus 3 will give us 1/2 x squared minus 3x. And then we have our plus c. So our function is f of x equals 1/2 x squared minus 3x plus c. So this is the general solution. And our general solution has infinite number of solutions because of c. C can be any number, which changes our function in many different ways, right? So general solution represents all of the possible functions that could be f of x or dy dx. Okay, in our case, all of our possible functions could be quadratic functions in this case. Right, so our general solution, the solution with the plus c, can mean a whole lot of things. There could be a whole lot of different functions that fit this function, right? So because of that, we can't actually put into our calculator to find the graph of this because c could be anything. This is how we get our slope fields. So for the AP exam, there are 4 things you're going to need to be able to do with slope fields. First, you're going to need to know how to sketch a slope field, which is what we're going to practice in this notes packet, given a differential equation dy dx. Second thing you're going to need to know is, given a slope field, you're going to need to know how to draw a particular solution. Thirdly, you're going to need to know how to match a slope field to a given differential equation, which we'll do a little bit of practice in this packet as well. And then lastly but not least, match a slope field to a solution of a differential. Okay, so we'll get practice in all 4 of those things, some of which we'll practice in this packet, some of which we'll just practice in class or while we're reviewing. Okay, so here we go. Given the differential equation below, we want to compute the slope for each point indicated on the grid to the right. Then make a small mark that approximates the slope through that point. So first slopes we want to find are when the slope is 0. Because when the slope is 0, our tick mark is just going to be a horizontal line. So we want to know when dy dx equals 0. That happens when x equals 1. So everywhere x equals 1, we're going to make a horizontal tick mark that represents a slope of 1. Okay. We also want to know when our tick marks will be increasing or when our tick marks will be decreasing. So we need to know when the slope will be positive or negative. So dy dx is going to be greater than 0 when x is greater than 1, and dy dx will be less than 0 when x is less than 1. All right, so now I'm going to show you how to actually find the slope of these lines. Okay, so if I go over here to 2, at 2, I'm going to plug in to my differential equation. So my x is 2, so I'm going to plug in 2, so I get 2 minus 1, which is 1. So that means the slope of my graph at 2 is going to be 1. So one thing that I can do is I can be accurate about it, right, and make a small tick mark at 2 for a slope of 1. Okay, and if I look, there's no y variable over here, so all of my x's at 2 will have a slope of 1. So I could use my ruler and do that. Okay, so now if I look at when x is 0, if I plug in 0 into my dy dx, I get 0 minus 1, which is negative 1. So now at 0, all of my tick marks are going to have a slope of negative 1. And I'm just estimating these slopes using the little dots on the grid. They help me a little bit when it comes to estimating. All right, at negative 1, if I plug in negative 1, I get negative 1 minus 1, which is negative 2. So here, we don't have to be as precise, right? I just know that the slope is steeper than negative 1. So, I mean, given the fact that I have a ruler, I can be more precise than you, but as long as your tick mark is slightly more steep than what you had before, you'll be fine. And then last but not least, negative 2 minus 1 is negative 3. So I'm definitely not going to use my ruler here. I'm just going to estimate it by just making my line a little bit steeper than I had previously. Okay. All right. So notice how the segments drawn on the graph above would form a parabola if they were connected. Right? So if I had said that on the f of x graph, the point negative 1, 1 existed. So if the point negative 1, 1 existed, then I would find or sketch the parabola for this by just following the tick marks, right? Whatever the tick marks do, that's what I'm going to do. And if you look, they create this type of parabola. Okay, so when given a slope field to draw a particular solution, you find the point that exists, and then you just kind of follow the tick marks, follow the curve that it creates to create the graph. Okay, so given the differential equation below, we want to compute the slope for each point. So again, we're going to find when does dy dx equals 0. That occurs when x is equal to y. So anywhere that x equals y, I'm going to create a horizontal tick mark. And on the AP exam, as long as you have those zeros, that's at least 1 point on the FRQs. Now we want to know when dy dx is less than 0, which is when x is less than y. And dy dx is greater than 0 when x is greater than y. So again, we can check some of these to see what the slopes will be. So at -1, -2, if I plug in -1, -2 into dy dx, I get a slope of +1. So I'm just going to sketch that. Okay, at 0, -2, I get a slope of -2, so, or +2, sorry. So I'm just going to sketch that a little bit deeper. And then it looks like the farther I go across, the steeper my line gets. And that's going to be the case for every line that's drawn. And then over here at the top, right, when x is less than y, these are all going to be negative slopes. So I can check these numbers by plugging them into dy dx, but I have already, and I know that this is generally what those slopes look like. For the most part. Okay, so sketching a slope field does not need to be precise at all. The parts that should be precise are definitely the zeros. Right? The zero slope should be very precise. You should know what those are and you should be able to label them. And the other precision that you need to have is the positive and the negative. Are your slopes increasing or are they decreasing? When it comes to drawing the actual tick mark, as long as the steepness, you can kind of see the steepness, then you're fine. Shouldn't be a problem. So for this problem, we're given a slope field and we want to find the differential equation that goes with it. So what we're going to do is we're going to determine some test points. Okay, so given all these differential equations, I want to pick a point on here where the slope is 0. So let's say I pick the point -1, 1. So my test point is -1, 1, where the slope is equal to 0. So now I want to check to make sure that when I plug in -1, 1 into any of these equations, I get the answer 0. So for dy dx for A, I have x times y, -1 times 1 does not equal 0, so A cannot be my answer. For B, I have -1 times 1, sorry, -1, which does not equal 0, so B can't be my answer. C, I have -1 times 1 plus 1, which does equal 0, so that's a possibility. For D, I have -1 times 1 plus -1, which does not equal 0. And then for E, I have -1 plus 1 cubed, which does equal 0. So C and E are possible solutions. Okay, so now I'm going to choose another test point, preferably another one that equals 0. So now I'm going to choose another test point where I have 2, 0, and again the slope equals 0. So I'm going to check C and E to see which one works. So for C, I have 2 times 0 plus 0, which equals 0, so that works. And then for E, I have 2 plus 1 cubed equals 0, which is not true. So C is my answer. Okay, so when given a slope field, you really want to just check for some test points. And unless it tells you that a point slope is 1 or 2 or whatever, the easiest test points to find are the zeros because they're the horizontals. So if you find a 0 test point, check it out, see if it works. If there are multiples that work, check another test point, see if that works. Okay, so the next two problems are both FRQs. So I'm going to basically walk you through how to answer an FRQ problem when it comes to slope fields. So for this first problem, I want to consider the differential equation dy dx equals x to the fourth times y minus 2. Usually in these cases, the first thing they ask you to do is to sketch the slope fields for the differential equation. So for part A, first thing I want to know is when dy dx equals 0. And that occurs when x equals 0 or y equals 2. So when x equals 0 or when y equals 2. Those are my zeros. I also want to know when dy dx will be greater than 0, which is when x does not equal 0 and y is greater than 2. So anytime y is greater than 2 and x isn't equal to 0, we're going to have a positive slope. And dy dx is going to be negative when x does not equal 0 and y is less than 2. Okay, so basically above here we have positive slopes, below here we end up with negative slopes. And I've already done the math to kind of know the steepness, right? Because at 1, 0, if I plug in 1 for x, that's a positive 1. And if I plug in 0, that's negative 2. So my slope should be about a negative 2 slope. All right, now part B. While the slope field in part A is drawn at only 12 points, it is defined at every point on the xy plane. Describe all points on the xy plane for which slopes are negative. Great, we've already done this part in part A. So we know the slope is negative when y is less than 2 and x does not equal 0, because x to the fourth will always be positive. And a positive times a negative is always negative. All right, now for part C, which is typically always in a slope field FRQ. You're going to have to find either the general solution or the particular solution for the differential equation. So in our case, we want to find the particular solution with the initial condition of f of 0 equals 0. So we have function dy dx equals x to the fourth y minus 2. So first step in solving a differential equation is separate our variables. So we have 1 over y minus 2 dy equals x to the fourth dx. And then we integrate. So when we integrate the left side, the derivative of y minus 2 is 1, right? So that means that this is an ln function. So ln of the absolute value of y minus 2 is equal to, and then find the antiderivative of this. That's x to the fifth 1 over 5 plus c. All right, so our initial condition is that f of 0 equals 0. So if we plug that in, then we have ln of 2, negative 2, sorry, equal to c. So ln of 2 equals c. So our function is that ln, the absolute value of y minus 2, equals 1/5 x to the fifth plus ln of 2. And since it's asking us for a particular solution, we have to now take the e of both sides. The e and the ln will cancel each other out, and we'll be left with absolute value of y minus 2 equals e to the 1/5 x to the fifth plus ln of 2. Rules of exponents, I can separate the exponent by multiplication. So I have the absolute value of y minus 2 equals e to the 1/5 x to the fifth times e to the ln of 2. E and ln cancel out, so I'm left with the absolute value of y minus 2 equals e to the 1/5 x to the fifth. And to solve this, solving an absolute value means that we have two possible options. So we either have y minus 2 equals e to the 1/5 x to the fifth, or we have y minus 2 equals negative e to the 1/5 x to the fifth. And if we solve here, okay, y equals 2 plus e to the 1/5 x to the fifth. And if we check our initial condition, 0 does not equal does not equal 4. I actually left out a number. So back up to here, e to the ln, the e and the ln cancel out, so we're left with 2. So I forgot to include that 2. My apologies. So then we have 2 plus 2 is 4. 0 does not equal 4. So because of our initial condition, we cannot have that side work. So now let's try the other side. We have y equals 2 minus 2e to the 1/5 x to the fifth. If we plug in our initial condition, 0 does equal 0. Therefore, f of x equal to 2 minus 2e to the 1/5 x to the fifth. Okay. So now for 2008, another slope fields problem. We have the differential equation dy dx equals y minus 1 over x squared, where x cannot equal 0. So we will not have any zeros in the denominator. So we want to sketch the slope fields for the differential equation. I actually want you to practice that on your own. So for A, Make note of all the things you need to know, and then do part A on your own. Sketch that slope field. For B, it wants us to find the particular solution, y equals f of x, to the differential equation with the initial condition f of 2 equals 0. So here again, we need to solve the diff EQ. So we have dy dx equal to y minus 1 over x squared. Separate the variables, and we have 1 over y minus 1 dy equal to 1 over x squared dx. And we can rewrite both of these sides. 1 minus 1 to the negative 1 dy equals x to the negative 2 dx. And when you integrate, the left side has an ln, y minus 1, and the right side is negative x to the negative 1 plus c. Okay, so what I want you to do from here is actually plug in the initial condition and actually find the particular solution for part B. I actually want you to do that part on your own. I've gone as far as integrating it for you. Now it's your job to do the algebra. Plug in the initial condition and solve for y. Okay. Part C. Part C, we want to find the limit as x approaches infinity of that particular solution. So if you did all the work, your particular solution should be that f of x equal to 1 minus e to the negative 1 over x plus 1 half. So if we're looking for the limit as x approaches infinity of f of x, that's the same as saying the limit as x approaches infinity of 1 minus the limit as x approaches infinity of e to the negative 1 over x plus 1 half. Okay, so we can separate exponents using multiplication here because our exponents are added. So we have the limit as x approaches infinity of 1, which is 1, minus the limit as x approaches infinity of e to the negative 1x times limit as x approaches infinity of e to the 1 half. Now, e to the 1 half is a number. So this limit is equal to just e to the 1 half, or the square root of e. So what we have is 1 minus square root of e times the limit x approaches infinity of e to the negative 1 over x. Now, if we put into 1 over x very, very large numbers, that fraction is going to approach 0. It just is. As the denominator of a fraction increases, the overall fraction approaches 0. So what we really have is 1 minus square root of e, and the limit of this is going to be e to the 0. Anything raised to the 0 power is 1. So we have 1 minus square root of e times 1. So our limit is equal to 1 minus the square root of